My name is Amitesh. I have a university-wide faculty teaching award at Princeton University for teaching linear algebra, and this is as part of a special lecture series on linear algebra lectures as I delivered at Princeton University on systems of three linear equations in three variables. We're going to start off by talking about how we solve it. We're going to talk about the conceptual mathematical framework, thinking about it geometrically, augmented matrices of systems of equations, reduced row echelon form, and row echelon reduction. It's going to be a tour through all of that in a mini lecture series style. So let's just dive right into it and start off by talking about this system of three linear equations in three variables. And I'm going to right now introduce or dive into the augmented matrix of a system. So when we have such a system of three linear equations in three variables, the important data is just the coefficients. We don't have to keep writing out the variables if we're trying to solve the system. So what we do is we start off by just writing out the coefficients of the variables in an ordered array of numbers, which is called an augmented matrix. So here I've just put a 1 here to say it's just 1x, and now we write out the coefficients 1, 2, 3, and then we write out 2, 3, 4, and then we write out 3, 4, 5. And we've separated a vertical line to denote that these are equal to constants, so they are not coefficients of variables, and they correspond to 4, 5, 6. And the process of solving such a system of equations is basically by eliminating variables. So what we can do, for example, is if we multiply the first equation by 2, we get 2x plus 4y plus 6z is equal to 8, and then we subtract from the second equation, we're then going to be able to eliminate the variable x in the second equation. Okay, so let's do that, and let's try to get used to this augmented matrix notation, because this is much more tidier once you're used to it, and it's an essential part of linear algebra. So what we do is we just say, okay, if I multiply the first equation by 2, then all the coefficients are going to multiply by 2. So instead of 1, 2, 3, 4, I'm just going to get 2, 4, 6, 8. Okay? And now, if you subtract the first equation from the second, you're going to get 3y minus 4y plus 4z minus 6z. So it's going to be minus y minus 2z is equal to minus 3. And if you sort of do it on the level of the augmented matrix, you're multiplying the first row through by 2, and then you're subtracting from the second row. So we put a tilde here to denote this is what is called a row operation, which is simplifying the numbers in the matrix. By multiplying the first row by 2 and subtracting from the second row, we're just going to get, on the second row, we're going to keep the first row the same, 1, 2, 3, 4. And in the second row, we're just going to get 0, minus 1, minus 2, and we're going to get minus 3. Okay, so here we've just subtracted twice the first row from the second. So what we can do is we can label this as the first row, the second row, and the third row. And here we've done the operation II minus twice times I. Okay, and so we get that, and we get 3, 4, 5, 6. Okay, so this is what is called a row operation. It's created a 0 here. And we'll see that by creating enough zeros, we can solve the original system of equations. So let's kind of modify the system as we go along to kind of see what's happening to the equations. So here I'm just going to return it back to its original because we're just keeping it that way, but I wanted to show it to you so you can see it being subtracted from the second equation. But here we have 1x, 2y, 3z is equal to 4. But now the second equation has become 0x minus y minus 2z is equal to negative 3. So we can write that down. It's going to be 0x minus 2y. So 0x, we can just remove it, and we can say it's going to be minus y minus 2z is equal to negative 3. And now we can go with the third equation. We want to keep eliminating variables. Okay, so that's the idea. We now want to eliminate the x again. So we do the same idea with the third equation, and we're going to see everything. So this is practice with augmented matrices, and we're going to talk about free variables, which are going to come up because this system of equations is going to have infinitely many solutions. So here what we can do is we can again think about subtracting the first equation from the third, or 3 times the first equation from the third to eliminate the 3x. So again, just for visual depiction, I'm going to show you multiplying the first equation through by 3 is going to be 3x plus 6y plus 9z is equal to 12. We subtract it from the third equation, so we can do again a row operation. Okay, so what we can do is now we can put another tilde here, and we're subtracting 3 times the first row from the third row. Okay, or 3 times the first equation from the third equation, and then we're going to get minus 2y minus 4z is equal to negative 6. Okay, so I'm going to write that down. It's going to be minus 2y minus 4z is equal to negative 6, and we're going to have a 0 here because we've eliminated the x. So we're now going to get this augmented matrix, which is a row reduction. This is what we call it. It is a row reduction, so it's the third equation minus 3 times the first equation here. and it is a row reduction from the original matrix, it has the same solutions as the original system of equations, because we're just changing them by adding them and keeping them together. So of course, if you keep the first equation and you introduce the third equation minus 3 times the first equation, that's the same. Saying those two are valid is the same as saying the first and third equations are valid. So we get an equivalent system of equations here. And now we see something super cool is we can eliminate again variables here. If we actually write out what this looks like on the left hand side of the board, we're just going to get minus 2y minus 4z is equal to negative 6. So minus 2y minus 4z is equal to negative 6. And now you see that the second equation and the third equation are very close together. If we try to actually eliminate the y, by what we can do is we can multiply the second equation by 2 and add it to the third equation. But if we try to do that, then what's going to happen is not only y is going to be eliminated, but z is also going to be eliminated. So that's super cool. So let's actually write that down. So here we've got that. If we now go back up, so I'm just going to erase what we originally had at the bottom and just show you the row reduction on the bottom matrix, augmented matrix down up top. Now we add twice the second row to the third row, okay, or twice the second equation to the third equation. So now if we go up top, we're going to keep the first equation as it is, 1, 2, 3, 4. And then what we're going to do is we're going to add this. So we're going to say twice of this is minus 1, minus 2, minus 3 is going to be minus 2, minus 4, minus 6, which is exactly the same coefficients as the third. So if we add them up, we're just going to get a bunch of zeros on the bottom. We're going to keep the second row as it is, and we're going to get the following augmented matrix. So here, you can say that you're just adding on for the third row, you're adding twice times the second row. Okay, so that's what you did from the previous step to get to your new augmented matrix. And this system of equations now, if you actually write it out here, all we've done is we've multiplied twice times the second equation and added to the third, we just get a bunch of zeros on the bottom. So we don't get anything, we just get 0 equals 0. It is a redundant equation. So actually we have 2 equations in 3 variables, and this is very interesting because now what happens is that z can be anything, and we can figure out what y and x are in terms of z. Now I'm going to do one more simplification, and that simplification is going to be putting it into what is called reduced row echelon form. Okay, so right now z can be anything. Once we know z, we can work out y, right? We can sort of solve for y once we know z, but z can be any number. There's going to be a y value, and once there's a y value by the first equation, the z value, y value are going to give an x value. Okay, so what we want to do is we want to say that z is what is called a free variable, and then we can find out what y and x are in terms of z. But instead of going through the first step, we have to write x in terms of y and z. I'm just going to write x in terms of z. That's what I'm going to do in this step. So I'm going to eliminate this 2 here, I'm going to add on twice the second row to the first row. Okay, so if you minus 2 from the 2 here, you're going to get 0. So twice the second row times the first row. So what we're going to get is we're going to get 1 plus 2 times 0, 2 plus 2 times minus 1, which is 0, and 3 plus 2 times minus 2, which is 3 minus 4, which is minus 1. And then we're going to get 4 plus 2 times minus 3. 4 plus 2 times minus 3 is going to be 4 minus 6, which is minus 2. Okay, so we're going to get this system here, and we're going to get 0, minus 1, minus 2, minus 3, and we're going to get 0, 0, 0 here, minus 6. Okay, so this is what is called the reduced row echelon form. So what we've done here is we've taken the first row and we've added on twice times the second row. Okay, so if we do that on this side here, we get x minus z is negative 2. So we've really simplified the system of equations here. We are not anymore dealing with a system where it's not obvious what the solution is. Now it's pretty obvious. And another thing you can do to make everything nice and symmetrical is put a plus 1 here, plus 2 here, plus 3 here. That's the same equation. If you just multiply by a minus 1 on the second equation, that's what you're doing. So I'm just showing you what's going on the augmented matrix side and the actual system side. And now we've got this very nice system of equations that we can solve by inspection. And this is what is called the reduced row echelon form. It is kind of the simplest way of writing out the augmented matrix so that you can actually see the solution by inspection. And what's the solution going to be? So this is going to be the concept of a free variable. So we're going to say that z, so these are basically corresponding to planes in 3-dimensional space. Equation between x, y, and z in 3-dimensional space is a plane in 3 space, and 3 planes are intersecting, okay? And the free variable is, we said z is equal to t. What that means is that z can be anything, okay? Because they're not, the third equation has become redundant. So once z is fixed as t, then y is going to be 3 minus 2t. So y is going to be 3 minus 2z, which is 3 minus 2t, and x is going to equal to minus 2 plus t, okay? So that's going to be x and y in terms of z. So we're going to get the parametric form for a line. Okay, that's going to be the solution. This is going to be the parametric form for a line, and we can write it out as follows. So 3 planes are intersecting in a line, and if you want the visual picture for that, think about like a book that is bound, okay, binding of a book. As you kind of look at the pages, they all kind of come out of the binding, and that binding is like the line that the 3 planes are intersecting in that one line, okay, and that line is parameterized by t, comma 3 minus 2t, comma t minus 2. That is going to be the parametric equation of the line that solves the original system of equations, and that's a solution. And here we say there's one free variable. So one free variable. Okay, so 3 planes are intersecting in a line. Now 3 planes typically will intersect in a point, just like 2 lines will intersect in a point. Check out my previous video. I've talked about systems of 2 equations in 2 variables. 2 lines can intersect in a point. They can be parallel, or they can be the same line twice. So then you'll have infinitely many solutions like you do here. But in 3 space, you can have 3 planes. They can intersect in a point. You can have 2 of them are parallel, and then there's not going to be any solution. Or you can have, for example, them intersecting in a line like we have here. Or you could have they're all the same plane, and then they intersect in a plane's worth of solutions. Okay, so that's the geometric side of it. So here we've seen this one situation where we solve the system and we got a line. Now what I'm going to do is, in a future video, I'm going to talk about this process more generally. Okay, so check out, this is a lecture series on linear algebra as I've taught at Princeton. Elite math education delivered straight to your room. So please like and subscribe so you don't miss anything. But I'm now going to talk about some reduced echelon forms. So we understand the process of simplifying matrices. I'm going to show you how you can see the solutions once you've simplified the matrices. So for example, what we can do is I'm going to give you, so we're going to play a game. I'm going to play around with some examples of augmented systems. So, if you're studying this stuff in high school, college, or just for fun, whenever you do these echelon reductions, you'll get down to a system, and knowing how to solve it once you've got down to it is going to be crucial. So here I'm going to write down some augmented matrices, and we're going to try to understand what the solutions are. Okay, so step 1, I'm going to write down the following augmented matrix. So it's going to be 1, 1, 1, and it's going to be 4, 5, 9. Okay. This is going to be our augmented matrix, so I'm going to put a 2 here maybe. And if you don't indicate anything, that's typically to indicate zeros. Okay, so if you see in linear algebra someone leaves without the zeros, they leave the matrix, that's just a bunch of zeros to be filled in. Okay, so now when you have this system, how are we going to solve this system, right? So we always work from bottom to top once we've put it in this simple form where you have these leading ones. Okay, so what's happening is that this equation is telling you that z is equal to 9. So we know what z is immediately. Then the second equation is telling you that y is equal to 5. And the third equation is telling you that x plus 2y is equal to 4. So now because you know y is 5, x plus 2y is 4, that means x plus 10 is 4. That means x is 4 minus 10, which is negative 6. Okay, so therefore x is equal to negative 6. So we found a unique solution to this system of equations. Notice there wasn't a bunch of zeros at the bottom. So in this system you had 3 1s, and there's going to be a unique solution in this case. No matter what's happening at the top, as long as the bottoms, you've got zeros here, you can sort of just work your way up like a ladder. Okay, that's the general idea here. And you can actually make this into an even simpler form like we did in our previous example. You can subtract twice the second row from the first. So if you subtract twice the second row from the first, what you're going to get, so I'm going to just erase this actually. So here this is 3 planes intersecting a point. I'm going to show you that if you subtract twice the second row from the first, then you're going to get, by doing that row operation, you're going to get 1, 0, 0. Twice the second row from the first is 4 minus 10, which is negative 6. And there you see the x is negative 6, right? So you kind of, once you've got it down in this form, 0, 1, 0, 0, 0, 1, this is what is called a, I'm going to define this precisely in future lectures, but this is called the reduced row echelon form, because you can literally see z is 9, y is 5, x is negative 6. The equations are given to you, okay? So that's going to be that example. Now let's do another example. So I want you to kind of play along with me, try to find out what the solutions is going to be to this augmented matrix or the corresponding system of linear equations. So we're going to write down the following. We're going to write down 1, 2, 7, and then we're going to have a bunch of zeros. 0, 0, 0, 0, 0, 0. Okay, and here we're going to have 3, 5, 8. Okay, this is going to be case 1. And case 2 I will show you. Okay, so this is case 1. And case 2 is going to be the same system, 1, 2, 7, 3. And check out my previous video on systems of two linear equations in two variables. We're going to see the same phenomena. And here you're just going to have 0, 0, 0, 0, 0, 0. What is the solution set going to be in each case? And this is actually super cool. So one thing that helps, when you're getting used to this notation is maybe just to write out what the system of equations looks like in each case, just to feel for what's going on. And we'll see that the solution sets are going to be very different, even though we've only really changed the last column, which is beyond the vertical line that is augmenting the matrix. So here in the top system, we have x plus 2y plus 7z is equal to 3. But then we have 0x plus 0y plus 0z, which is just 0, is equal to 5. And we have 0 is equal to 8. This is what is called an inconsistent system. It doesn't make sense. There is no solution. Okay, so here we will say there is no solution. When you do your row reductions and you have a bunch of zeros in one row and then it's equal to something non-zero, that can't have any solution. Okay, so that's no solution. What about the bottom one? Okay, so we've seen the case where we had infinitely many solutions, where the solutions are parametrized by a line. 3 planes intersecting in a line. You can also have 3 planes intersecting in a plane, as I said. Let's have a look at this. You've got x plus 2y plus 7z is equal to 3, just like before. But now you've got 0 equals 0 and 0 equals 0. That's perfectly fine. They're redundant. Okay, so here you have basically two equations that don't give you any information. Only one equation gives you information. So here the question for you is, how many free variables are there? How many variables do we need to know to figure out the last variable? So in the first example we did, we needed to know one, which was z, and then we could figure out y and x. But in this example, we actually have to know both y and z. Then only can we figure out x. So actually you have what are called two free variables here. Okay, so I'm showing you all the phenomena of different kinds of systems of 3 equations in 3 variables. And this is going to really prepare you for future kinds of more complicated augmented matrices and row echelon reductions to deeply understand the processes here. So here we're going to have two free variables. You can set y is equal to s and z is equal to t. Okay, so we're just putting a parametrized form. So once y is s and z is equal to t, we get x plus 2s plus 7t is equal to 3. So therefore, x is equal to 3 minus 2s minus 7t. So your parametrized form is going to be 3 minus 2s minus 7t, comma s, comma t. Okay, so because you have two free variables, your solution set's going to have dimension 2. That's also a fundamental concept in linear algebra. It's going to come up a lot. It's related to the rank nullity theorem. So all these phenomena we see in systems of equations are going to motivate a very deep and sophisticated mathematical subject. But here, once you have s and t, we know the third variable, so it's 2 dimensions. There are 2 parameters you need to specify a point that is a solution. And that means it's going to be a plane of solutions. Okay, so that's another example. So I've just summarized different systems of 3 equations in 3 variables, started off with one and talked about what kinds of phenomena can happen. You can also have no solutions, as we talked about. This is the case where they're like parallel planes in some sense. And you can also have like a line's worth of solutions or a plane's worth of solutions or a unique solution. So talked about all of those in this video. In future videos, we're going to talk about row echelon reduction, and we're going to talk about what is a reduced row echelon form, theorem proving why rigorously that any system of equations has a reduced row echelon form, and diving deeper into that as I've delivered at Princeton University. So thank you so much for watching. Before you click away, I wanted to tell you I'm creating free accessible math education. I believe that everyone in the world should have access to math education, no matter their background or their personal circumstances. And although right now I'm constrained by internet access, I'm trying to give everyone who has internet access free accessible education. And as my channel grows, I will try to diversify to beyond that once I have more resources. So if you want to support my vision, if you're enjoying my content, it's benefiting you, there's math at all levels, from basic algebra all the way up to very high level, graduate level math. I'm delivering math over time. I'm a research mathematician, so I spend my time thinking about math, solving unsolved problems, and I'm putting a unique angle to math as a journey rather than as a bunch of concepts. So thank you so much for watching. I wish you all the best, and I'm super excited to see you in the next video. Please take care. I'll see you soon. Drop a comment down below if you have thoughts or questions, and I'm looking forward to seeing you in the next video.